Okay, so this is now that we know how to find the mean and the standard deviation, and we've learned how to use that to describe our data. Now we're going to look a little bit more about at what else can we do when we know that data is distributed a certain way. And the one that we're going to talk about a lot is normal distribution. If something is normally distributed, we know a whole lot of stuff about data. We can make predictions about the data. Okay. And I will tell you already, normal distribution, you should be thinking bell curve. Right? This is the big thought here. You should be thinking bell curve. And in a nutshell, I'll try to make this very simple. The mean, the average is always going to be at the center. And you have most of your points clustered around the center. You have some that are far below and some that are far to the right. But when normally distributed, we have this. Okay. What is not normally distributed, perhaps? Let me give you some examples. This is what a we're going to look at that a bit closer later on. But this would be if you were to graph a curve, let's say you have your frequency here and whatever else here. Let's say it's time, dismissal time at Sisler. 3:30 comes around. I don't think it's a normal curve. I've been stuck in traffic many times. I think it's more like this. Right? Everybody kind of gets picked up at the beginning. And then it kind of slows, then the traffic slows down like that. You don't have the slowly you're being picked up and then it's a peak. And then it's more like this, most likely. I mean, some get picked up earlier, you can argue, but this would be a skew. This is not a nice bell curve. It's not a hat, right? The Mexican hat, right? And then you could have instances where, right, the curve is more like this. Right, it's more skewed towards the right. This one is more skewed towards the left, right? But when you observe, when we graph things and it appears to look like this, like a smooth bell curve, this is a normal distribution. And this is what we're going to kind of park on for a little bit. And then we're going to analyze data and see, does it look like this? Does it look like this? Or is it actually normally distributed? Okay, that's where we're going. But we're going to park here and assume everything we do is normally distributed. Okay. Let's keep going here. I'm going to highlight a whole bunch of stuff here. So watch this. It is a probability. It is a probability distribution that is symmetric. There's so many key terms here, but everything is connected. You will see that after. It is symmetric about the mean. So it's symmetric around the mean. Losing it already. Okay, showing that data near the mean are more frequent. Data near the mean are more frequent in occurrence than data that's far from the mean. Okay, in graph form, right? A normal distribution looks like a bell curve. There it is again. The mean indicates the location of the curve along the x-axis. The mean indicates the location along the x-axis. That's very important. And I have my iPad ready to go here. I'll show you that. What does the standard deviation tell us? The standard deviation indicates the scale along the x-axis. Mean is where is it along the x-axis? Standard deviation is this scale. Bigger scale, it'll be spread out. Smaller scale, it'll be closer together. I'll show you that with an interactive normal distribution in a bit. A large standard deviation, maybe I'll switch colors here, right? A large standard deviation will stretch the curve, it flattens the curve, right? While a small standard deviation will squeeze the curve and it'll be steeper. And I just want to show you that when I make these booklets, I think big picture. Okay, this is after years and years of me teaching this. Let's see here what I mean by that. I'm going to try to find that page more at the beginning. There was this one on page 3. I was already hinting towards that. You don't have to go there right now, but I'll maybe make a reference. See page 3. I was already talking about that here. I was already giving you I was foreshadowing what we're doing later on. Okay. So I need to go back to 24 now. I will just say see page 3, right? If you want to see more like a visual of the two different scenarios, I have one on top, one at the bottom, kind of separating them, okay? Symmetry indicates that half of the values are below the mean and half are above, okay? That's important. So symmetry tells us that half are below and half of the values are above. That is symmetry. It's like your parabola, same thing. Examples of data that follows a normal distribution. So there's a lot of human characteristics, right? Like you have the height, our weight, migrations of birds, right? The geese, there's some that come early and then slowly it kind of amps up and then there's that peak date. They study this, right? Like they can see that. Baby birds hatching in the spring, right? You've got some early starters and then you have more and more, right? Even geese, right? You see them with their little ones. You see at first just a couple and then you see more and more. Time of the year, does are in heat, like female deer, right? There's that peak. Some get earlier, some go in heat later, okay? Amount of traffic around certain time of the day, building up to that rush hour, right? Number of COVID admissions to the hospital, and so forth. Is it perfectly normally distributed? Not always. But if it's close enough, we still call it normal distribution. So this is very important to fill in. And make sure you fill this in right, okay? So let's make sure we understand that this is our mean, okay? That is our mean. So that's mu, right? It's like meow. That's cat language for normal distribution. So that's the mean or the average. Okay, that's very important to know that. Okay, I'm going to use that same. So it could be that the average height for a certain country is like along the, imagine this is your x-axis, right? The higher the average height, the further to the right this would shift, right? And everything would kind of gather around that average height. If you have a different country that has a shorter average height, you would go down the x-axis. So this bell curve would follow you there, okay? And then the gaps that are formed here is what we call the standard deviation, okay? So let's look at it this way. If you go from the average and you go one standard deviation to the right, or you go one standard deviation to the left, we know that there's a 68% chance that a person will fall within one standard deviation of that average height. And you're like, Mr. Dixon, I don't get it. The one standard deviation thing, I don't know what you're saying here. Remember the bowling example that we just did? One of the teams had a 20 standard deviation, right? Team B. So that would be like if the average is 140, then plus 20 would be 160, right? To the right, scoring up to 160, and then taking away 20 would be 120 on the low end. So there's a 68% chance that the team would score anywhere between 120 and 160. And if you're still like scratching your head, I'm going to do an example in a bit, okay? But there's a 68% chance that scores will be between here. If you go further, if you go one standard deviation and then another one, so within 2 standard deviations, there's a 95% chance that you would fall anywhere between here and here. Okay. And then if you go 3 standard deviations to either side, so minus 3 standard deviations or plus 3 standard deviations, you would think it's 100%, but not quite. It's 99.7% chance that you fall within 3 standard deviations of that average. Okay? Just follow for now. So frequency, right? Frequency is how many people would be there, right? How many people would be in there? And this could be height, this could be hours, whatever we're going to be talking about, it's going to go along here. So I just want to make sure also you understand that, let's make an arrow here. Curve never touches x-axis, okay? Just by definition, it just never touches the x-axis. There's always a chance that a person might be outside of the 3 standard deviations, or an animal or object, whatever, right? So we never touch the x-axis, okay? That's very important there. And along the x-axis, you might have height, weight, volume, time, etc. Okay, so that that's dependent on the problem, the context at hand. Okay. But if you look at the whole curve, guys, you know how it's only 99.7%? The whole curve, it's 100%, right? It covers 100%. The probability that you are within this curve is 100%. Everybody fits in this curve somehow, okay? So let's talk about symmetry. If this is symmetric, if we know that this is 68, then it stands to reason that this little chunk will be 34 and this little chunk will be 34 as well. That's an estimation, by the way. Later on with the calculator, we will find out exactly. It's very close to 34%, okay? It then stands to reason that this is 13.5% and this is 13.5%. And you're like, wait a minute, how so? How so? Well, 13.5 plus, let's just add 68 here, plus 13.5 is 95%. So all of these little areas here still add up to the 95 that we have on top, right? That go from here to here. And next is 2.35. So this is very small. I apologize. This is 2.35% here. And this is 2.35%. I hope you can see that. 2.35. I'm saying that over and over is to make sure you get that right. This is 2.35. And then last but not least, outside the 3 standard deviations, I'm just going to say that this is 0.15%. And same here, 0.15%. So it's a small chance that data would fall outside the 3 standard deviations. Okay. Another thing I need you to know is that if this is the center, then we know that 50% of data will be to the left, like if you consider the whole curve, and 50% would be to the right, okay? So the mean is your middle, okay? Once we do examples, it will make a bit more sense once we do a couple of examples here. Next thing I need you to add is, so you're gonna have, these will actually be numbers down the road, okay? Like actual numbers, not the standard deviation attached to them. But this is important. Next thing we have is z-scores. So just imagine a German scientist saying z-scores, right, or something like that. But z-scores, that's probably how they came up with that. So this tells us how many standard deviations you are from the mean. So if you're right on the average, you would be 0 standard deviations away from it. If you fall right under this value, you are +1 standard deviation from the mean. If you fall right here, you are at +2 standard deviations from the mean. If you fall right here, you are at +3 standard deviations from the mean. So there's a relationship between the actual value that's going to be here and it has a z-score that's attached to it. And I'm focusing on the ones that fall exactly on this line here. Are there z-scores for everything in between? Yes. There will be decimals down the road, but not yet. If you fall right here, you would be at, your z-score would be exactly -1. If you fall right here, your z-score would be exactly -2. And -3, of course, for this one. Let's finish this page here and then we'll do an example so that this whole mumbo jumbo will make more sense. So if you're a little bit like, I don't know, I'm just copying right now. For now, that's what you need to do. Just copy, make sure you have everything. And then when we do the examples, you might have to refer back to this curve. Okay. Next, some observations. The percentage in each section represents the likelihood, right? Percentage in each section is the likelihood or probability of data falling, right? Data falling within that interval. A normal distribution, right? A normal distribution, I'm going to use a different color just so it stands out. A normal distribution follows the 68, 95, 99.7 rule. It is also known as the empirical rule. Okay? A larger standard deviation results in a flatter curve. Data is spread out. Is dispersed. I just like to use different words to mean the same thing. Okay? If it's a smaller standard deviation, it's a steeper curve. Data is clustered around mean. Remember, the standard deviation is always with respect to your mean. The standard deviation is always like, how are the points related with respect to that average that we found out, right? So the total area or probability under the curve is always, watch this, 1 or 100%. And why am I saying that? Well, if you use decimals, then it'll have to add up to 1. But if you just stick with the percentages up here, it should add up to 100%. Okay. So write that down. I'm just going to give you a quick interactive scenario here with that bell curve, because unfortunately this one is static, right? We can't move that. But so here, imagine this is my average here. Let me see. Okay, it's very exciting stuff, right? But this is my average. This number right here is my average. So you could, the average could be higher or lower for a class, right? It could be that this class gets an 80% average, or it could be lower. It doesn't matter, but your curve would move along the x-axis if you move the average. If you were to now calculate your standard deviation, the greater the standard deviation, the greater that scale, right? The scale along the x-axis. right? A bigger number will make the gap wider, therefore flattening the curve. Okay? But remember, under the curve, everything under the curve is always 100%. Always. So if your standard deviation is smaller, I like that as a teacher on my tests. I like to see that because I have most students closer to that average that I'm after. So I don't have the very low, very high, all over the place scattered, right? And then I can work with maybe, hey, maybe let's do some more activities or different lessons to bring up the average, but everybody comes with, because the way I'm teaching is pretty standard, right? Everybody kind of just goes along with what I'm doing, right? Kind of indicates how clear your message is, right? If you're teaching and you get boom, boom, boom all over the place, like, wait a minute, something is wrong with the way I'm communicating. You're obviously some are not getting it and some are getting it, so something is wrong with that, right? So keep that in mind. The curves, unfortunately, when I make them, they all look kind of the same. But in reality, if you were to scale them properly, they would be steeper or flatter depending on the situation. Let's keep going and do one example here. I'm going to skip calculating z-scores by hand for today because I want to dive into this example here. Okay. The height of males in Canada is found to be normally distributed. To us, that means way more than just fancy words there, right? Like, oh, normal distribution. I know what the graph is supposed to look like. I know something about the 68, 95, 99.7 rule. There's a lot of things I know just by reading these two words. Next thing, the mean height is 177 centimeters. And the standard deviation is 2.5 centimeters. Okay, so I will ask you to draw a normal curve and fill in as much information as possible. So the percentages, you need to have that on your study sheet. Okay, how to do that. So let's fill this in. We have 68, 95, 99.7%. That's a given. Okay, I don't need to tell you that. Normal distribution tells you that. Along the mu, you do not have to have these on your graph, okay? This is just to guide you. But along, right at the center, you're gonna have 177 centimeters, right down the center. So write that down, right? 177. The x-axis represents the height in centimeters. And this would be frequency, in this case would be number of males, okay? There you have it. But you're not done yet. This is where you just have to use your standard deviation to come up with the other numbers. Because it says from 177, if you added one standard deviation, so plus, what is my standard deviation? It's 2.5, right? We're told it's 2.5. So this is then 179. Have your calculator, because sometimes these numbers are very weird. Like, you don't want to make a mistake on those, right? So you grab your calculator, you go plus 2.5. That's 179. 179.5. Okay? Then you keep adding another standard deviation to get to the next number. This is basically your scale. This is your X scale, guys. That's what your standard deviation is. Let me zoom in a bit because I feel like I need to. So another 2.5, that'll be 182. And then you add one more time. This could be done in your head for sure, but plus 2.5. This is 184.5. And remember, these are centimeters. Right? Let's go left. If you go to the left, this is your x-axis, so this is going to go down, right? So you go minus 2.5. So you go 177 on your calculator, 177 minus 2.5. That's 174.5 minus 2.5. 172, right? So you take away 2.5. 172. Take away 2.5 one more time. 169.5. Again, you don't need to show me these arrows down the road. You do not need to do any of that. It's actually you're gonna be really quick at it. You're just gonna go add, and so forth. I need you to understand though what we're doing here. I really need you to understand this. 3 standard deviations. What is that? Watch this. If you were to go 177 plus 3 standard deviations, like I'm literally saying the mean plus 3 standard deviations, you should get 184.5, which I did, right? So from the mean, adding 3 standard deviations would get you 184. Mean adding 2 standard deviations would get you 182 and so forth. Okay, so that's what this is trying to tell you. Okay, let's fill in the rest. This is 34 and 34. This is 13.5 and 13.5. This is 2.35. I just memorized these, but then again, I've seen it many times, right? So I don't know what you need to do. If you need to write those down on your study sheet. And then this would be 0.15% under that sliver. I had to work so hard to make sure that it doesn't touch the x-axis. I had to like zoom in and fill in with white to make sure there's a gap there. Okay, so this would be a pretty good normal curve, all filled in. However, I'm missing something. It says include z-scores as well. Include that. So that's actually not too bad. You go under the average, you go 0, 1, 2, 3. And then you go -1, -2, -3. Sorry. I need to edit my booklet. That's what I need to do. Give more space. And make sure you just write down z-scores here. I like you to have the correlation between the actual height and what kind of z-score that would represent in this case. Okay. Okay, let's answer some questions based on this. So once you have this filled in, if I say use the graph, please use the graph, because down the road you might not have to. Using the graph will answer the following. Okay, so you have to use that graph. It says, what percentage? Can I say it a different way, guys? What is the probability? It's the same thing. What percentage of males? What's the probability of a male having a height between 172 and 179.5, right? So what is the probability of that happening? And you say, hey, this is a min and this is a max. So 172 is right there, and 179.5 is right there. So what you need to do is take these are your 2 limits, and you're going to add the percentages that fall from this to this, okay? The percentages that are associated along the way, that's what you're going to add. So it's 13.5% plus 34 plus 34, and you know that's 68, right? 34 and 34 is 68, right? And so this ends up being 81.5% of males there's a chance that they are between these 2 heights. That's how big the chances are, right? This is the likelihood or probability. Okay, let me zoom out there. So there's a likelihood that a random male in Canada, if you ask, right, there's an 81.5% chance that that person is between these 2 heights. How do we know that? Because we were told that as normally distributed. Right? Next, What percentage of males are expected, what happened there, to be taller, sorry guys, to be taller than 182 centimeters? Taller than 182. There is no max, right? It just says taller than this. So you just go to 182, and it would literally be 2.35 plus 0.15, right? Because taller than this would be here, and everything above it would be considered taller, right? So you would go 2.35% plus 0.15%, which is 2.5%. Chance. Okay? And it's probably true, right? My height is 195 centimeters. So yeah, there's not many of me walking around in Canada, right? So yeah, the likelihood of that is small. There's a small chance of that happening. What percentage of males are shorter than 169.5 centimeters? Watch this. There's this one condition, shorter than this or taller than this. What is happening there? Here you have to be creative. There's many ways of doing this, okay? I will show you one way. Okay, so let's see where we're at. Shorter than this. So let's go find 169.5 is right here. So you want everybody that's shorter than that or taller than 179.5, like taller than this. So in a sense, you want to add this percentage and all the percentages to the right of the 179.5. So all of these sections here are going to give you that answer. So shorter, let's just make an arrow. That would just be 0.15%. Taller than 179.5, that would be 13.5 plus 2.35 plus 0.15. What does that give us? 2.5, that's 16%. And the word or, remember this for grade 12 applied. Or in math is adding. It's this or that, which means we got to combine that. Okay, so 0.15 plus 16, that would be 16.15% chance. Okay, the probability, the percentage of that happening, right, is that. Could there have been a different way? The answer is yes. Pay close attention, listen closely to what I'm about to say. You know that everything under the curve is 100%. You could have actually went 100% minus these sections here, right? So if you subtract what doesn't apply, you would have been left with everything else, right? You would have been left with shorter and taller. So you decide how you want to approach this. Do you just want to focus on getting the sections, adding them up? Or do you want to use 100% and subtract what doesn't apply? All right. Let's keep going. 26E. Are we almost done? Wait, you know what? Can I ask you a big favor? You just make sure you read this over. Add the percentages to your study sheet and try page 26. I have a feeling that you'll be able to answer more than what you think. Okay, so I'm just going to say page 26. I am certain you're not going to be able to answer everything because I didn't cover that. I skipped a little part there. But let's get your brain thinking about this. Thank you, guys.